At the dawn of the 20th century, classical physics reigned supreme, yet puzzling experiments, like the way objects radiate heat and how light interacts with matter, hinted that reality at its smallest scales was far stranger than imagined. The revolution began in 1900. Max Planck, struggling to explain blackbody radiation, reluctantly proposed that energy isn't continuous, but comes in discrete packets or quanta. 5 years later, Albert Einstein took this further, suggesting light itself consists of these quantum particles, which he called photons, brilliantly explaining the photoelectric effect. The old rules were starting to crack. Niels Bohr then applied these quantum ideas to the atom in 1913, picturing electrons in specific, quantized orbits, explaining atomic stability in spectra, but it was still a partial picture. The true upheaval came in the mid-1920s. Louis de Broglie daringly proposed that if light waves can act like particles, then particles like electrons must also act like waves. This wave-particle duality became a cornerstone. In 1925, Werner Heisenberg formulated matrix mechanics, a radical new mathematics for quantum systems. Almost simultaneously, in 1926, Erwin Schrödinger developed wave mechanics, introducing his famous equation describing how quantum wave functions evolve. Max Born then interpreted these waves, stating their squared amplitude gives the probability of finding a particle, injecting inherent chance into physics. Heisenberg's 1927 uncertainty principle cemented this strangeness. There are fundamental limits to how precisely we can know certain pairs of a particle's properties, like its position and momentum. The very act of observing changes the system. Finally, Paul Dirac unified quantum mechanics with special relativity in 1928, leading to the incredible prediction of antimatter. These breakthroughs, though often counterintuitive, laid the foundation for our modern understanding of the subatomic world, underpinning everything from lasers and computers to the ongoing quest for quantum computing. Quantum mechanics didn't just solve old puzzles, it unveiled an entirely new, probabilistic, and wondrous reality. When we gaze at images of the night sky, we're often captivated by the brilliant tapestry of galaxies, but between these luminous structures lie the universe's greatest, most enigmatic expanses, cosmic voids. These are not just empty patches, they are colossal, underdense regions, the silent giants of the cosmic web. Imagine the universe as a gigantic frothy sponge. The dense parts of the sponge, the filaments and clusters, are where galaxies congregate, drawn together by gravity. The vast interconnected bubbles within this sponge, those are the cosmic voids, and their scale is truly mind-boggling. Typical voids can span tens to hundreds of millions of light-years across. To put that in perspective, our own Milky Way galaxy is about 100,000 light-years wide. You could fit thousands, even millions, of Milky Way-sized galaxies side by side across a single large void. Some supervoids, like the Eridanus supervoid or the Boots void, nicknamed the Great Nothing, are even larger, stretching for hundreds of millions of light-years. While they're called voids, they aren't entirely empty. They do contain some galaxies, often called void galaxies, but these are much sparser and more isolated than those found in denser regions. Interestingly, these void galaxies often appear to be younger and bluer, suggesting they are still actively forming stars, perhaps because they experience fewer disruptive mergers and interactions compared to their counterparts in crowded galactic clusters. Cosmic voids also play a crucial role in shaping our understanding of the universe. Their very existence and properties provide strong evidence for the standard model of cosmology. The way they've grown over cosmic time is sensitive to the nature of dark energy, that mysterious force causing the universe's expansion to accelerate, and even the mass of neutrinos. Studying the subtle distortions of light from distant galaxies as it passes near or through voids, weak gravitational lensing, can help us map the distribution of dark matter. One fascinating, though still debated, idea is that cosmic voids might even exert a subtle push on surrounding structures due to their lower-than-average density, contributing to the large-scale flows of galaxies across the universe. So these vast expanses of near-nothingness are far from boring. Cosmic voids are fundamental components of the universe's grand architecture, holding clues to its past, its evolution, and its ultimate fate. They are the quiet, immense backdrop against which the cosmic drama unfolds.